Guys, welcome to our resonance structures workshop. I'm gonna go ahead and refresh my page now. We are streaming live. Thank you so much for joining us. My name's Johnny from Clutch Prep, and this is Jonathan. Jonathan,
hey guys.
We're the organic chemistry tutors here at Clutch, and Jonathan's gonna be in the background taking care of everything, answering your questions in case I can't see it.
Yeah.
So I just wanted you guys to know who Jonathan is when he messages you. Okay, Jonathan, thanks for helping us out.
Right, cool.
And now I'm going to introduce what we're doing. Okay. So yeah, go ahead and refresh the page. Make sure that you can see me, that you can hear me. If you're having any tech issues, let us know so that Jonathan can start trying to fix things. Okay, we want to make sure this session's going great. How's it going, everyone? It's so great to see you guys. First of all, let me do some shout outs really quick. I saw Katrina from FIU, Katie from MS State, go Bulldogs. Who else? There was Prita from Penn State. Guys, there's a lot of people all over the country watching this live stream right now, and I just want you guys to know that my job is to help you guys get a better grade on your next organic chemistry exam. This session is going to be totally awesome. I'm going to kill resonance structures for you guys so that when you get to when you see a resonance structure in your exam, you're excited that you have one because you know how to do it so well, okay? Just to introduce what we're doing today, this session will probably be anywhere from 90 minutes to 2 hours long. We're going to go over a 20-question packet, and in that packet, I'm going to go over the easiest questions first, and we're going to, Jake from State Farm, we're going to be going over some easy questions, and then slowly building up the difficulty so that by the end of today, you're doing some of the hardest resonance structure questions possible. If we have a little bit of time, I'd also love to take a few questions from the class. You guys can just let me know, hey, I have this specific problem that I don't know how to solve. We really can't go over 2 hours today because I have another session after, but I'd love to help you guys if we have a little bit of extra time at the end, okay? So guys, there's a packet that we're going to be going over, and it's what you see behind me. So let me just put my mouse here so you can see. It's these types of questions. So it's like this and this. We're going to be going over these together. If you want to take notes on the packet, there's a link below this screen where you can print out the packet. But if you're at school and maybe you don't have a printer around, you don't have to print it out now. You could print it out later. Another thing about this session is that it's going to be available for replay later. So I would love for you to stick through the whole 2 hours, but if you have to leave a little early, it's okay. You can watch it later, okay? So guys, a little bit, just so you guys know about resonance structures, it is for Orgo 1 and it is for Orgo 2. If you happen to be here and you're in an Orgo 2 class, you're saying, do I really need to know this? You do, because resonance structures is one of those topics that you need for all of Orgo 1, and in Orgo 2, it's extremely important for conjugation and aromaticity, which are topics that are about to come up for the Orgo 2 students as well. So this is one of those rare topics that everyone needs to just refresh on, and that's why we're going to do it together in a group. Okay? So, guys, I just want to introduce myself really quick. My name's Johnny. I've been tutoring organic chemistry for 10 years. And I used to just do a lot of private tutoring. And then I realized that I could help more students by building the video version of your textbook. So that's exactly what I've done with Clutch. With Clutch, we make the video version of your textbook so that instead of having to read the textbook, you can watch me explain it to you in an easy way. And today what I'm going to do is I'm going to explain resonance structures and do a bunch of problems. And I'm just hoping you guys will learn and ask me questions. I can see exactly what you're writing as soon as you write it, so I'll try to respond as much as I can. Okay? Cool. So let's go over the very first question. Let's just all start, and I'm going to be reading as I go, but I want to get the session started now, okay? So what is the definition of a resonance structure? Let's just start off real easy. Compounds with the same molecular formula? No, that's not it. Compounds with different carbon frameworks? That sounds like an isomer. So I'm going to go ahead and say it's not that. Structures that differ only in the placement of pi and non-bonding electrons? That sounds pretty good. Let's go ahead and check that for a second and read the fourth one. Structures that differ only in the locations of bonds? That's not right because we know that in resonance structures, bonds and lone pairs can move. So I'm going to go ahead and X all these out. The right answer is C, structures that differ only in the placement of pi and non-binding electrons. What that means is that pi bonds are double bonds, and non-bonding electrons are things like negative charges, lone pairs, positive charges, and radicals. That's exactly what we do when we're building a resonance structure. We're showing how all of the electrons from all those different types of species will blend together and will hybridize, okay? So that's what we're going to be doing today. We're going to be looking at electrons, not moving atoms, okay? Now, there's a question now here below that we'll go to next, which is a pretty easy question. But before that, I want to show you guys some of the most important rules for resonance. I have these 3 rules for resonance that we're just going to write together, that after we write those rules, we're going to use those rules for the entire session today. So are you guys ready for the 3 rules of resonance structures? You need to know these. 1, so I'm going to just start right here so we can draw it together. 1, atoms can never move. Okay, what does that mean? Guys, when you're moving atoms from one place to another, that makes what's called an isomer. An isomer is when atoms are connected to different places. So what we're looking for with resonance structures is that all of the structures have the same exact atoms in the same exact order. The only difference is the electrons, the double bonds, the negative charges, etc. Okay, so that's one thing. Okay? 2, your arrows. So this has to do with the arrows that you use for mechanism. Your arrows must move from negative to positive. Okay? Your arrows must move from negative to positive. So that means that if you're contemplating, where do I start my mechanism arrow from? Always go to the thing that has the most electrons. So if there's a negative charge, start from there. If there's a double bond and no negative, start from there. But you should never start from like a positive charge. So what I'm trying to say is that you're usually going to be going from something negative to something positive. From something that has the electrons to something that wants the electrons. And then lastly, this is a good check just to make sure that you got your structures right. Net charges of all structures must be equal. Okay? So what that means is that, let's say you drew out 3 structures and you're trying to make sure, are all these structures really resonance structures? You add up the charges of each one, and if they have the same charge, that means you probably got the right thing, okay? But if they have different charges, that's a warning sign that you drew it wrong, okay? So guys, I see that some of you guys are having some tech errors, and a lot of it can just be fixed by just refreshing the page, but it might have to do with internet speed. Maybe if your internet speed is a little slow, it might just be best to watch this later for on the replay. I hope that it gets fixed for you guys, but if anything, know that all of this will be recorded for you later, okay? Cool. So guys, here's a really easy question to start off. Draw the appropriate arrows for the following resonance structures. So what we see here is that we're moving positive charges around, okay? So whenever you're moving, so these are the 3 rules, but then there are also 3 patterns that we're going to be talking about today of resonance structures, and one of them has to do with moving positive charges. So I'm just going to put here pattern 1. And this is the pattern we're going to use probably for the first hour. We're just going to be doing a lot of this. Pattern 1 is when you're moving positive charges. When you're moving a positive charge, where do you think you want to start the arrow from? Do you want to start the arrow from the positive charge or from the double bond? Which one has more electrons? The double bond, right? Because double bonds have extra electrons inside of them, and positive charges are missing electrons. So we would start the resonance structure from here, and we would move it into this bond. Okay? What this would then give us is now a new resonance structure that looks like this, where now the double bond is here, and the positive charge is here. Okay? So that is pattern 1, and what we notice is, how many arrows did you use for the positive charge? We only used 1 arrow. So when you're moving positive charges, we're going to use 1 arrow because you can just swing the electrons into that positive charge. One thing that I like to say is it's like you're opening the door. It's like you're swinging the door hinge. So whenever we do with positive charges today, we're only going to be using 1 arrow, and that's going to apply up here. What type of charges are we moving? Positive. So that means we're just going to be using 1 arrow every time. let's go ahead and use this pattern and see if we can get this question right. So let's look at the first one. I see that I have a positive, and then I have this double bond, and then I have this double bond, which I'll make blue. And then I have obviously my positive. Let's make the positive green. So for my first resonance structure, where do you think my arrows should be involved? Where do you think my arrows should go to? Should they start from the green and go to the yellow? Should they start from the blue and go to the green? Like, when you're first learning resonance structures, it's really hard to know where to start sometimes. So where do you guys think, according to the rule I just talked about, where do you think it makes the most sense to start this first arrow from? Yellow to green, right? Because what I want to do is I want to move from high to low. That's the first thing. So I see that the green is my low, and my yellow is the closest high. Blue is also high, by the way, but blue is really far. Why would I start all the way over there? That's going to be like a really long arrow. It doesn't make a lot of sense. So I need to go from the closest high to the closest low. So how many arrows am I going to use? 1 or 2? 1, right? Because this is a positive charge, so we know you can just swing it open like a door hinge. So let's go ahead and swing it open up that door, and what we're going to now get is this resonance structure, which actually is already drawn for us. So there's nothing to do here. Usually, your professor will ask you to draw the resonance structure, which we'll do later on. But this is just like an easy one, so it's already drawn for us, okay? Cool. So guys, now notice that the locations of things have flipped a little bit. Now let's say this is my green, this is my yellow, and then this is still my blue. Notice that what I did is I flipped the positions of the green and the yellow because they now switched, okay? What do you think would be another resonance structure that I could draw to complete this? What would be the next one? Where should the arrow go from? So everyone's saying blue to green, which is awesome, and that's exactly right, because what we want to do is we want to show how this charge can flow through all the double bonds possible. So what I want to do is I want to show from blue to green, again, 1 arrow, and what that's going to do is now that's going to basically invert the whole thing. Now I have yellow here, I have blue here, and now my green is over here. And by the way, guys, like, those two are done. Now all I need to do is show how this resonance structure above me can go back to the one that was the second one. So then what that means is we're going to have to go backwards a little bit. What arrow should I show so that I can show how this one above me goes back to the one in the middle? What do I need to switch? So actually, guys, it would be blue to green again, right? It would be that now I would start from this blue and go to this green. Because what that would do is it would go back to the original. Okay? So these are resonance structures, and we're actually done with the question, which is cool because we applied the same rule and we got the same answer every time. But I'm not just here to apply these rules. I'm here to really help you understand it. So there might be some people in the crowd. There are a lot of people slowing down everyone's internet. Maybe some of you guys are saying, but Johnny, there's this other atom over here that's in pink that was never involved. Like, you never actually drew an arrow to it. Why can't I make a new resonance structure that takes electrons from here and like makes a double bond there? Why is that impossible? Why didn't you draw that? And guys, the reason is because, yeah, there's no double bonds, there's no source of electrons that you can actually use to put electrons into that positive, okay? So what that means is that you need some source of electrons to draw an arrow. You can't just start from single bonds. You can't break bonds. Right here, this carbon looks like this. It looks like carbon, hydrogen, hydrogen, hydrogen. That's what it looks like when you draw it out in Lewis structure. Let's say that I drew that I want these electrons to come in here and make a double bond. That would be moving a hydrogen, because now I would break the hydrogen bond. That hydrogen would have to pop off, and now I just created an isomer, which is not what I'm trying to do, right? So that's why sometimes you reach the end of the road and you can't make any more resonance structures. The reason is because you don't have any more electrons that you can use without breaking a bond. Making sense so far? Cool. So already you're thinking, I could do this. Let's see if we can apply this to a second structure with positive charges and if you guys can get it faster. So let's go ahead and scroll to the next page and see if now we can draw these from scratch ourselves. So this says draw 2 resonance structures for the species below. And now this is where you guys are going to help me, because notice that in this case, I gave you the middle structure. So now I want to know what's the structure on the right and what's the structure on the left. And I'm also going to use the color system again so that everyone's on the same page. Why don't we make the positive green again? Why don't we make this the blue double bond and this the yellow double bond, just in this case, okay? So if I wanted to draw the structure on the right, what would that arrow look like? How should I start that arrow? Yeah, you guys got this. So we've got yellow to green all around the country. Everyone's saying yellow to green, which is a great feeling because that means that everyone's learning this type of resonance structure. So I would go from negative, which I'm saying from the double bond, which has more electrons, to the positive, which has less. And what I'm going to do is I'm going to draw my new resonance structure that looks like this. Now, what does it look like? Because now this time we have to actually draw what it looks like. So then it would be the double bond is now here and the positive charge is here, right? So that means that now this is blue, this is yellow, and this is green. Now, by the way, once your positive charge reaches the end of the structure, you know that's the end of the road for that positive. So that's easy. I don't have to think about are there more structures I could draw to the right side? Obviously not, because that's the end of the road. So now I have some questions. I want to make sure I answer them. Could you also do blue to yellow or no? But then he said blue to green. Got it. So yes, you could. And that's actually going to be the other structure we're going to draw on the left side. If the positive went the other way, that's what we're going to do now. So a bunch of people are asking just different things. So can you watch it after? Totally. This is all going to be recorded. You could watch it as many times as you want all semester long. Some people are wondering, like, why do I have like a sad face next to my name? Guys, that's just because our website automatically generates a picture for you if you don't upload your own profile picture. So if you don't want a sad face next to your name, just upload whatever picture you want. Or you can keep the sad face if you really do feel sad right now, which I felt sad. I would feel sad before this lesson, but after this lesson, you're going to feel awesome. Let's go ahead and draw the other resonance structure, which would be the arrow going from blue to green. So then that would be this. Let's not draw the double bonds yet. Let's just draw the framework, the carbon framework. Cool. I'm just drawing the backbone, and then we can decide where the double bonds go. So I know there would be a double bond here. And then there would also be a double bond here now, right? With a positive here. Because they switch places. So now this is still yellow, but now this is blue, and this is green. Got it? And yeah, it is free. It's going to be free all semester long. This session, however many questions we do, it's all free, okay? Cool. So guys, those are our 3 resonance structures. Is anyone wondering if I can maybe put the positive charge here? Is that possible to move the positive charge down to the bottom? So it's not, because guys, there's no electrons. There's no electrons that can be used to transfer the positive. Exactly, good. Does it matter if you draw the extra line for the double bond above or below? Oh, that's such a great question. Guys, I know that a lot of you are brand new to organic chemistry, so it can be confusing. For example, what's the difference between drawing my line here for my double bond or drawing my line here? Does anyone know? Which one is more stable? I'm kidding, guys. They're both the same thing, okay? It doesn't matter. It's just a matter of personal preference. I don't even know what I just draw it next to it. It's exactly the same, okay? So it doesn't matter where you put it. Cool. Good question, though. And if you have any questions like that, I really hope you guys will ask. For the third structure, how come the positive charge isn't on the 4th carbon instead of the 5th? It's hard for me to know which one you mean is the 4th carbon, Prita. But think about it this way. They have to swap perfectly, right? So if the double bond went on these 2 here, your positive has to go here. It has to go to the end of the double bond. There's nowhere else that it can go, which is why I drew it there. Okay? So can you explain why the positive charge can't move? Yes, exactly. I would love to. I'm going to try to do this quickly for you guys, okay? So guys, just so that everyone's clear, I want no one to be confused about this on the test. What do the hydrogens look like at the bottom of the square? It looks like this and like this, right? In order for that positive charge to move down, what would need to happen? I would need to take the electrons from here, from one of the hydrogen bonds, and give them to the positive. What is that going to do? That's going to break the bond to the hydrogen, and now I'm moving an atom. What was rule number 1 of resonance? You can't move atoms, right? So that's impossible. That's why it has to just, it's stuck there. Okay? Cool, and I see that you guys are all trying to help each other out, which is awesome, because we might be going too fast for me to answer everyone's question, but if you guys can help each other, then we're solid, okay? Cool. All right, let's keep going, guys. So let's do another one. They're going to get progressively harder and harder, okay? Cool. So which are correct resonance structures for the following organic compound? So here, guys, are our options. We're going to look at these at the end because I don't really need to see this until the very end, okay? Let's look at the bottom, which is the part that's important. So what I want to know is that this is how you could be asked on a test in a multiple choice way. You have your original resonance structure, and then your professor is going to ask you which of these resonance structures is valid, right? So what we need to do is think, how could we swing that door? How could we swing doors open or move electrons so that we can make some of these structures down here, okay? So let's look at one structure at a time and see, can we create that structure? So for one, I see that at first I see that this double bond hasn't moved. This double bond is the same. This is my green positive charge. I'm going to keep making the positive charge green just to be consistent. But then notice, guys, this is the first time, so this is a little different. This is the first time that we're going to deal with lone pairs. Okay? So this is where things change a little bit, and it's not hard, it's just a new thing that you need to know, okay? Which is that lone pairs also count as electrons you can move, right? So what I'm going to do is I'm going to put the electrons from the O as yellow, because these are available to potentially move, and you know what, why not? Let's make the lone pair from the nitrogen pink, just in case we can move that one too. So now we have more to think about, okay? Now the way that you move electrons from lone pairs into a positive is the same way that you move the door hinge, except it doesn't look like a door, it's just one arrow though. So one potential way that you can do this, you can take, because oxygen, according to formal charges, which is something that you guys learn in chapter 1, oxygen has 2 lone pairs, okay? Now if that's confusing to you, that oxygen has 2 lone pairs, it's totally fine, I get it, but I have other videos that help to explain that, okay? So that's a chapter 1 concept. And what you can do is you can take those lone pairs, one of those lone pairs, and you can give it to the bond that has a positive charge. So notice again, we're using one arrow, and what we're going to do is we're going to make a double bond. So what that means is that now the yellow electron is now here, because that's the one we took from the lone pair. This is where my positive is now, and the pink didn't move. Don't freak out, guys. It just shut off for 1 second. The camera shut off for 1 second. Cool, I'm trying to look here. How do you know that there's a lone pair on the nitrogen? Guys, the nitrogen has 1 lone pair because nitrogen likes to have 1 lone pair and 3 bonds. And that's just something that we learn in chapter 1 of your textbook. And I have a lot of videos explaining that. So you can get this information like in another lesson, okay? And I'd be happy to help. So then we're gonna move that there. So that means that is structure 1 possible? Absolutely, because we took the electrons from the O and we made them into a double bond, okay? So now let's see, okay, so structure 1 is possible. Is structure 2 possible where, actually, let's see. What's the best way to do this? So the best way to do this is to say, okay, is structure 3 possible? Because structure 2 is the most complicated one. It has the most movement. So now let's look at structure 3. I'm going to erase these lone pairs. We know that they're there. And I'm going to keep the colors consistent. And what I want to know is there any way, so we know 1 is possible, is there any way to move the electrons so that they turn into 3? What would I have to move? Good, because I would have to just swap the blue and the green, right? So let's do that. I'm going to draw that another one is that this could go like this, right? And notice what happens if your negative goes to the positive, you're going to get this, right? Because now your blue is here, your green is here, your yellow is still here, and your pink is still here. Is this making sense so far, guys? So what we just did is we just drew 1 and 3 perfectly. 3 used the old rules, 1 used the new thing with the lone pair, okay? Now I see, I'm gonna try to do number 2 and then I'll look at your questions, okay? Now for 2, the question is, can we then turn this, 3, into 2? What do you guys think? Is 3 gonna be able to turn into 2? And how would that arrow look? So let's go ahead and try it together, because this is exactly where students get caught up, okay? So the nitrogen here has how many hydrogens on it? It has 2 hydrogens, right? Now look at this one. How many hydrogens does it have? 1, right? So how did 2 hydrogens turn into 1? And the answer is you can't. 2 is a trick answer because they're breaking rule number 1 of resonance structures, which is that you can't move atoms. There's no way to turn 3 into 2 because the number of hydrogens is off. So this is not a proper resonance structure, even though it looks tricky. It looks like, oh yeah, I could draw that. No, you can't, because you just broke rule number 1 of resonance structures. So now we know that resonance structures 1 and 3 are possible. So let's figure out what answer choice that is. And that would be answer choice C, 1 and 3. Cool? So now I'm going to read some questions. Cool. How does it travel so far from Mizu? So allylic, vanillic stuff. So allylic and vanillic are words I'm not going to be using a lot today because they're a little bit complicated, but it's very possible for a positive charge to move all throughout the whole molecule. So that's where the concept of conjugation comes in. Maybe you're in Orgo 2 and you're thinking about conjugation. It can keep going throughout the whole molecule as long as it has a pathway. It's like a highway for the charge to go through. Can you please scroll back down? I'm right here helping you out. We will talk about hybrids towards the end of today, okay? Cool. All right, guys, so I'm going to move on to the next one. Cool, so circle the structure below that is not a resonance form of the structure in the box. So then, yes, awesome. I'm glad to hear that this is helping, guys. Okay. So circle the structure below that is not a resonance form of the structure in the box. So what we need to go through is go structure by structure and see if we can move any electrons to create this, okay? To create these different resonance structures. So let's start off, and probably the best way is to just start off with the very first one and figure out, is there a way that we could use arrows to make that thing? And what I see is yes. What I see is that I could take the electrons from this double bond and I could give them to the O. When I do that, what that's going to do is it's going to take electrons away from this carbon, which is blue. So now this blue carbon has a positive because it's missing electrons. At the same time, it's going to give extra electrons to the O, so now the O is going to have a negative charge. Notice that everything else stayed the same, so I'm going to go ahead and give this a check mark. This can work. Okay? Cool. Awesome, guys. And by the way, if you're just joining, don't worry about missing problems because this is all going to be broadcasted later and you can see it as many times as you want throughout the semester. So you can just go ahead and rewind it later, okay? Cool. So now let's look at the next one. Is there a way to make that structure into B? What I'll make as B. And what I see is that some of it looks possible. So for example, well, actually, it doesn't look very possible. That's the problem. Because in order to do this, notice that they have a negative charge on this carbon, right? Okay? Now the way that the negative charge on a carbon works is that this carbon right now has 3 H's. 1, 2, 3. Okay? Now, let's draw those 3 H's here. 1, 2, 3. Okay? The only way that you can make it negative is if you remove one of those H's and put a lone pair on it. Whenever you see a negative charge on a carbon, it means that you're missing one bond and that you have a lone pair on it. So, is it possible that I have these 3 H's, 1, 2, 3? Is it possible to have a resonance structure that only has 2 H's? What do you think about that? Is that a good resonance structure? No. So it's deceivingly, it looks good. Like if on the surface level, you might think, oh yeah, that could be a resonance structure, why not? No guys, it broke rule number 1, right? So it can't be, so we know that B is actually the answer, it's not a resonance form. But let's go through the others and just make sure that the others are possible. Cool. So let's go to C. How could we make C? Well, actually, that one is very possible. Because what you could do is you could do this resonance structure first, where you get the positive here and the negative here. And then once you have the positive there, what can you do? You can swing the door open. So you can swing this door down, and that's going to put the double bond now here and the positive here. So C was just a variation of A. That's fine. Cool. Another one that we see is that now for D, actually notice that the double bond O stayed the same. So in this case, I'm just going to use yellow here. This part is exactly the same. The only thing that changed is that the double bond on the top is now broken up into a negative and a positive. Is that possible? Yeah, you can do that. So what you could do is you could take this double bond and give the electrons to the carbon that's right on it. Guys, that's the only, when you break a double bond, you can break it into charges that are next to it, but you can't go further than that. So if you're breaking it into a negative here and a positive here, that's fine, because those were on, those ions or those charges were on the double bond to begin with. But you can't just like put it somewhere else. So this is fine because all I did was I took that double bond and I gave all the electrons to one atom and I gave none of them to the other. Okay? Now finally, what I see is that this one is more similar to this guy right here, right? It's got the negative charge. So is there a way that I could turn structure C into structure E? Look at structure C and say, how could you turn structure C into structure E? What could we do? So what we could do is we could take the electrons from the O. Remember that the O has 2 lone pairs that we were doing before with the other problem? This is the same thing. We're going to take one of the electrons and make a double bond here. Again, only one arrow because we have a positive charge. And that's going to give me this guy right here. So all 3 of these are possible, but the one that is impossible is B. Okay? I'm going to look at some questions now. So it makes the central carbon have a lone pair? Yeah, actually, that's exactly what happens. Remember I said that if you have a negative charge, it's a lone pair? So in this case, this carbon right here would have a lone pair. But that's okay because that's not changing the number of hydrogens that was there to begin with. Notice that this carbon right here has 0 hydrogens because it already has 4 bonds. This carbon here, 0 hydrogens. So we didn't break the rule number 1. We just changed the way that it looks. We moved some electrons around. Okay? How do you know if the arrow moves electrons to the vertical or in... Yikes. Okay, so Sarah, I want to help, but I don't understand your question, okay? So try to reword it a little bit. So, why does the O on the bottom of letter E have a negative charge? Great. Okay, guys, I'm just going to erase a little bit of stuff if you guys don't mind. If you want later on, you can draw all this, you can watch the recording, and draw all this again. But I think that all these markings are getting confusing, so I'm going to erase them for a second. So someone just asked me, which is a great question, why does structure E have a negative charge? Guys, that just goes back to what I said at the beginning, that the very first step of structure E was that this had an arrow here. Now, if I want to draw all the arrows for structure E, this is what it looks like. This one broke here, then this one came down, and then this one came down here. I've been talking about each of these arrows individually, but this is what it would look like if it was all one structure. You would draw all those arrows, and what it would show you is that now I have the negative charge here, and this double bond that's yellow is now here, and the electrons from the O that were green are now here. Does that kind of make sense? Which is the most stable in the box? The one in the box or E? Guys, that's what the end of today is going to be about. We're going to talk major and minor contributors. But first, we just want to make sure we can do our resonance structures. Cool. Awesome. No problem, guys. I think that we're making progress. We're moving forward. Awesome. So let's go ahead and look at this question. Which choice best describes the relationship that exists between the pair of structures below? Another way that your professor could ask in a multiple choice setting. Now, I actually think this is going to be a pretty easy question for you guys, but at the beginning it might have been a little bit harder. What do you guys think the answer to this question is? We're not going to have to solve it, really. Hey, you're from, so for this trash talking that's going on, you're from Missouri. That's not much better. So, anyway, so what is this relationship? So are they identical? No, definitely not. Are they constitutional isomers? So guys, constitutional isomers means that you're moving atoms, okay? Did any atoms move here? So for example, notice that this N has one H, this N still has one H. This O is just attached to a carbon, this O is just attached to a carbon. Nothing moved here. There are no atoms moving, so this is not constitutional isomers. But the answer is what moved? Electrons. Electrons moved because what happened was that the electron from the N made a double bond, and then this double bond came up and made a negative charge. So then this relationship would be resonance structures. Cool. I was waiting for you guys to answer, so I just kept explaining. But I think a lot of you guys knew from the beginning that this was resonance structures. A lot of people use Clutch at Hunter, so I'm pretty popular over there already, but I'd love to visit one day. Cool. You guys are in Manhattan or New York, right? I would super love to visit. All right, so let's keep going to the next one. Cool. So guys, this is getting, oh, what do they mean about identical? I'm sorry. I'm just going to go back to that question really quick, Josh. Identical would literally mean identical. It would mean that it would be this structure if it had a double bond here and a lone pair here. And a single bond here. Does that make sense? Like if you just flip the molecule but it was the same thing, that would be identical. Cool. Does that make sense? Identical means identical. There's no trick answer to it. Cool. Draw 3 other important resonance contributors for the molecule below. See, we're getting harder. I told you guys we're going to get a little harder every time, but notice that we're also still doing positive charges. You guys might be wondering, hey, is this all there is to it? We still haven't done negative charges or radicals yet, so that's why you have to pick out the pace a little bit so we can get to negatives and we can get to radicals. But you guys should be able to do this one pretty easily. Why don't you guys take a minute to start drawing the first structure on your own, and I'm going to start drawing structures as well, but try to do it on your own. No, I think it's going to be this way. don't worry about what I'm doing, guys. I'm just trying to set it up so that it will look clean. But however you draw your arrows doesn't matter, as long as you get the structures right. That's the important part. So guys, since we have a positive charge present, how many arrows do you think I should be using? Uno, right? It's just gonna be uno. And I know that I should start, like, now you guys have seen this pattern a few times, so maybe you guys can tell me. I have, let's do colors, yellow, green, double bond, blue, and then pink is gonna be the positive charge this time. So how do you think that I should start off this resonance structure? This is the most important step. If you can do this step, the rest is easy. But I want to make sure you guys can do this first step. What is the first step? What is the positive charge on? It's on the oxygen. So the oxygen itself right now is missing a lone pair. It has only one lone pair. So according to the formal charge rules, it's missing an electron. But that, guys, there have been a few questions on formal charges today. And if you search in the clutch chat bar, you search formal charges, I have a ton of videos making that easy for you, okay? Yeah, that's the rule. You got it, Josh. 6 minus 3 sticks minus 2 dots equals 1. There you go. So blue to purple, or blue to pink, you guys all got it right. So then it would be this double bond adds its electrons to the O. So now what I'm going to get is this structure. By the way, guys, that was awesome. The fact that all of you guys got that, that's the hardest step. If you know that step, the other ones are easy. So now I'm going to draw a double bond, double bond. These didn't change. Single bond. Now this part changed. It's OCH3. But now, what should I draw? I should now draw that my double bond is gone because now it became a new lone pair. So now there's a lone pair here and there's a lone pair here. By the way, you don't have to draw both of those lone pairs. That's implied. I'm just helping you guys see it. But if you didn't draw the lone pair, that's fine. Now, where's the positive charge? Here. They switched places, right? Whenever you move a double bond, you have to put a positive charge where it moved from. Okay? So remember that you start from negative to positive. You always go from negative to positive. Cool. So now we have that structure. Let's put our colors in. Yellow. Now this is actually, this lone pair is blue now. This is pink or purple, and then this is green. Cool. Okay, so now it's time to do the others, guys, and I hope that you guys will see that now it's easy. This is just like easy going. We're gonna go, one resonance structure is gonna be that the double bond moves in here. So let's draw that out. OCH3. So now this double bond is the same. Now here I have to draw a double bond here and positive here. Let's just go ahead and do our colors again. So you guys can easily visualize what's happening. And we know that the same thing could happen at the bottom. So we've got OCH3. The other way that it could go is that this double bond, yellow, goes to pink, which is what some of you guys were saying as well. Okay, green to pink or yellow to pink. So then what's going to happen is that I now have this double bond doesn't move. This double bond moved here, and now I have a positive here. And I'm just going to put in all the colors so you guys can see what's happening. And there you have it. Those are all the structures possible. Okay? Now, I'm going to stick on this for a while because this is a pretty hard problem. I'm going to answer some questions. Okay, why couldn't our first step be green to blue, then purple? Oh, so that's a great question. So some of you guys might be thinking, Johnny, I see what you're doing, but couldn't you do this instead? Couldn't you make this double bond go here and then this go here? Put two of them together. So guys, the answer is technically yes, but what you're doing is you're putting two resonance structures together, so it's more difficult to visualize. If you want to do it that way, it's fine, but then you're going to have to go backwards to flip it back. So what I'm trying to do here is I'm trying to use only one arrow at a time so you can see exactly where it's going step by step. But if you want to combine a bunch of them together, you could. It's just going to be a little bit hard to look at. But that would also be a right answer. Uh-oh, so it sounds, so for the blue, can you write a negative or put the lone pairs? Sure, I can, but just so you guys know, in bond line, which is what we're using today, you never have to write lone pairs anymore, ever, which is cool. Like when you're using bond line, it makes organic chemistry a lot easier once you don't have to think about them. You can just imply that they're there, but I'm totally gonna add them just to make it easy for you guys to relate. But one thing I try to do is train my students to get more and more comfortable with bond line so they don't have to rely on drawing them every time. Cool. I'm missing a carbon. Oh shoot, I totally am. Thanks guys. Tutors can make mistakes too. So there's the carbon. Wouldn't we get the same structure as the closest to the right? Guys, okay, so this is a great question. So, no, I mean they are different structures because one of these has a methyl or a CH3 here, and one of these has a CH3 here. They are different. But just so you guys know, if two resonance structures look exactly the same, you still should draw them both because your professor wants to see all the possible flow of electrons, even if they look the same. So this is the one situation where if you have two things that look very similar, you should still draw them both. Cool. Yeah, so you guys got it. There was a carbon missing. Thanks for calling me out on that one. And please, if I could make little mistakes here and there. Cool. So guys, is this making sense? I'm going to move on to the next one. But I think that, let me know if you have specific questions about how this could be improved. Do you need to put any charge or lone pairs on the oxygen? They're already there. I just did all the lone pairs and there's no charge. Oxygen, just so you guys know, this goes back to formal charges. Oxygen with 2 bonds and 2 lone pairs is neutral. So that's why there's no charge. Because notice that for all of these I have 2 lone pairs, so we're fine. Cool, and I see people calculating formal charge the way that we do it here at Clutch, which is awesome, because that's actually the easiest way. Cool, so let's move on to the next question. Ooh, boom. Guys, we're done with positive charges. You guys have officially, positive charges rest in peace. Now we have to go ahead and do negative charges, okay? So guys, what's the difference between negative and positive? Yeah, I'm going to help you guys. You know what? At the end, I'll include links for all the topics that we talked about today. If that would be helpful, I can just link everything. Cool. Awesome. So, guys, so are the 3 rules the same? Rule 1, Rule 2, rule number 3. Are these going to be the same for negative charges? Hell yeah. This applies to every resonance structure, so that doesn't change. What's going to change is the pattern. Pattern 2. Now that we have negative charges, pattern 2 is going to be a little different. What it's going to be is this. Let's say you have a double bond and you have a negative charge and you're trying to move it. Can you just move it by doing this? Why would that not make sense? What's a little bit kooky about that? I'm not starting from the most negative thing. Remember that you have to start from negative to positive. In this case, the negative is the charge. So I have to start from here. But another thing is that if I just use one arrow, I'm going to break the octet of this carbon. If I just were to use one arrow. So that means that when you have negative charges, you have to use 2 arrows. Okay, and I'm going to show you how to use those arrows now. One of the easiest ways to do this is to draw the hydrogen here so that you guys can visualize what's happening. So when you move this, by the way, pattern 2 applies to negative charges and it applies to lone pairs. Anytime that you're moving free electrons, you're going to use this pattern. Actually, let me go ahead and move this over here so you guys will know. Sorry. It applies to negative charges and lone pairs. Okay? So when you're moving them, exactly, when you make a bond, you have to break a bond. Let me explain why. This negative charge is going to make a new double bond here. Okay? You're going to make a new double bond there. But if you make a new double bond, let's just write it right there. What's going to happen to that H, or to that carbon? Now it's pentavalent. That means it has 5 bonds. Does that make any sense? hell no. Even though there was just a scientific paper that came out that says that you can make carbon have 6 bonds, which is crazy, but that's like cutting edge science, okay? Don't worry about that. But for organic chemistry 1 and 2, carbon has 4 bonds always. Like, can't make more than 4, okay? So what we have to do is we have to break a bond. So if we make this bond, we have to break this bond. And that is going to preserve the octet of that middle carbon, okay? So what that means is that after I draw my resonance structure, what I get is something that looks like this. Oops, the double bond is now here, and the negative charge is there. Okay? Being called an octet violator is like one of the biggest insults you could give to anyone. Please, let's refrain from using such language on this chat. I don't want to hear anyone being bullied online being called an octet violator. Okay, cool. So guys, so now we would have the negative charges over here. Notice that everything switched just like the positive charges, except that we had to use 2 arrows, and that's what we're going to be doing above. Okay? Cool. Awesome. So let's go ahead and start with the top structure. How do you think we could draw some of these resonance structures? So what we see here is that we have a negative, and we need to move towards the double bonds. So let's go ahead and draw some of these out. I've got yellow, I've got blue, and I've got green, which is my negative charge now. Now, by the way, guys, this goes back to my explanation. The negative charge means that you have a lone pair present. So that means the same thing. If you see a lone pair on a carbon, or if you see a negative charge on a carbon, those are the same thing. In this case, we just included both, so you'll understand. Okay? Is everyone cool with the fact that this means the same thing? Negative, if I drew, let me just be really, really clear with you guys. If I drew this negative charge, that's the same exact thing that I have drawn right now. If I drew this with a lone pair, that's the same exact thing that we have right now. All we did is we included both. We put the lone pair and the negative charge, so you guys know very well that this is a negative charge. Okay, cool. So what would be the best starting to these arrows? What's the first resonance structure I should draw? You guys tell me. Man, we got some proud Nittany Lions over here. I haven't visited Penn State either, but I'd be down. Okay. So I see this cyberbullying continuing, guys. I'm gonna have to shut this session down if it continues. So guys, what would be the best one to start off with? Green double bond to blue O. Yeah, I mean that would work. But also, guys, we could also go green to yellow. So anywhere that's starting off with green, going to either blue or to yellow, we're gonna draw both. So what we're gonna do here is, once again, guys, remember, you can't just do this. Please don't do that. You're gonna get no points on the exam. That would be terrible. What you wanna do is go make a bond, break a bond. You get that? Make a bond, break a bond. That's the pattern we use for negative charges. So what I would do here is I would go ahead and draw this. Now what this is gonna look like is a little different. Notice that now I'm gonna have a double bond here, and now I'm gonna have O negative here. Now what you do is you flip you swap the position of your negative and your double bond. So that means that now what I have is that this is still yellow, but now the green is here and the blue electrons are here. Cool? Make it or break it. How would you do both? You make it and you break it, not make it or break it. Okay, so the other structure would just be the opposite. It would be that the negative comes here and breaks this bond. So we're gonna get something like this. This one stays the same, this H is still there, but now I have double bond here, negative here. So that means that now this blue didn't change. Now green is a double bond, and now yellow is up here. Cool. Awesome, guys. So is this making sense? So notice how if I would have started off with this at the very beginning of the lesson, you guys probably wouldn't have felt as comfortable. But now that we know what we're looking for the 3 rules and we're looking for the patterns, it's coming together more. And we're going to keep increasing the difficulty. Cool. I don't know, guys. Like, I don't know why organic chemistry has to be so hard. I personally love organic chemistry, and I don't know, we just have to, like, just show people how to think about it, and it becomes way easier. So that's what I'm trying to do here. Cool, so let's keep going, and this is going to be a good question. It's a really, really long one. Oh, wait, I'm sorry. Would the negative charge have a preference between aldehyde and ketone? Philip? So, Philip, just so you know, the answer is kind of yes, but again, that gets into major and minor contributors, which I'm going to try to do later today. We've spent an hour here. In the next hour, I'm going to help you with strategies to answer that question. Which one is more stable? Cool. Cool. And by the way, if it's easy to understand, you're doing better than a lot of people. Because for a lot of people, they struggle to understand orgo. So if you're understanding it in class, you're off to a great start. Cool. So this is a question, by the way, guys, all these questions came from old exams from professors around the country. This question comes, I believe, from Professor Bachnack in University of Texas. So we're trying to like throw a bunch of different things at you so you can see the ways that different types of professors ask questions. So this is the way that Professor Bachnack asks it. Consider the anion below, I'm just going to read this really fast, which is a resonance hybrid. Only one important resonance structure is given. Each additional important resonance structure only has one atom with a non-zero formal charge. Whatever. Several of the carbon atoms in the given resonance structure are labeled. Which of these carbon atoms have a negative formal charge on it in any of the additional resonance structures that are not shown? Pick the one choice below that best answers this question. So this could be a hard way to ask this question just because it's hard to keep track of what they're saying. So basically, guys, we have 4 carbons. We have, and I'm just going to circle them, 1, 2, 3, and 4. And what this question is really asking is, when you draw your resonance structures, which of these carbons will get negative charges on them? The only way to know this is to draw it out and see where the negative charges land. Okay? So, how do you access the other videos? So actually, guys, this is a really great opportunity since we're right at the hour mark. Just give me 2 minutes to explain because people have been asking, okay? So just to introduce myself once again, my name is Johnny. I've been teaching organic chemistry for 10 years to students all over the country. And what we did here at Clutch that I'm really proud of is we built the video version of your textbook. So instead of you having to like read each chapter and get confused with the way that it's worded, I hate the textbooks. They teach very poorly in my opinion. I recorded videos to help you understand each chapter. So a typical chapter will be like anywhere from 3 to 6 hours of me just teaching like page by page pretty much. This is what you need to know. These are better rules than the ones that your book teaches you to understand. A lot of students around the country have used Clutch to get better grades, and every day I get texts like, thank you for saving my grade, etc. So the way you get access is to go to Clutch Prep, make a free account, select your school, select your textbook, and then you can see all the chapters for your textbook right there. You click on the chapter you want to learn, and it's me teaching you, okay? And this chat is always there, so you can always ask me questions as you're watching videos, etc. I have it on everything, guys. I have it on every single chapter all the way to the end of Orgo 2. Bronzed-Lowry acids, I kill Bronzed-Lowry, okay? So, and just so you guys know, there's actually a special, so the way that it works is that about half of the videos are free. Me doing the concept videos and teaching you, those are free. The ones that you have to pay for to watch are a bunch of practice problems. And the reason, guys, is because we have to pay the bills here. We have about a staff of about 20 people that work so that we can keep these videos online, so we can make the website better, so we can make this resource available to you. So to get unlimited access to all the videos, it's anywhere from about $15 to $30 a month, but there's a lot of free stuff that you can watch, including just like a lot of concept videos if you want to just use the free version, which I totally understand because I was a college student not that long ago. Okay, by the way, there's a special discount that's just for you guys today and next week for our second part of our live stream. By the way, this is a 2-part live stream. Next week we're going to have another one. And the discount is arrows 20. And the reason I called it arrows 20 is because this week and next week we're going to be drawing a bunch of arrows. So it's just specifically for people that have been watching the live stream, arrows 20. And what that gives you is 20% off any subscription that you purchase. So basically whatever the price would be for that month, it would just be 20% off, which is really helpful because I know you guys are all about saving money and being, frugal. Cool. Awesome. And if you just purchased it, it's fine. You can, you actually could unsubscribe and use the code for the next month. So it applies for all of you guys. It just means that you would get your discount next month, Irene, okay? Cool. Awesome, guys. So that's basically the way Clutch Prep works. And now I explained how you can watch my other videos. Basically, organic chemistry is like 60 or 70 hours of videos of me teaching you guys Orgo. Okay, cool. So let's go ahead and answer this question. We have to draw the resonance structures. So how do you think we should use one arrow or two arrows for this? Oh, by the way, I wanted to just say one more thing, which is that even if you're not interested in purchasing Clutch, which is totally fine, I get it, we're gonna have a free live stream next week that I'm gonna talk about at the end of today's session. So please stick around for another hour. We're gonna be killing resonance structures, and I'm gonna talk about what part 2 is, because this is actually part 1, where we're talking about resonance. Part 2, who knows what it's going to be? I know. I'm going to tell you at the end of today's session. And it's going to be also 100% free. So if you just want to log in and learn with us next week, I'd love to see you here. So, guys, so the way that this would work is, should we use one arrow or two? We should use two because we have a negative charge, right? So what we would need to do is start drawing resonance structures. So we would have to start from the double bond that's closest to the O and move that. Basically, you'd have to start from the double bond that's closest to the O and use the negative charge to move into it. So what would be the pattern? It would be make a bond, break a bond, right? Now, some of you guys might be wondering, Johnny, could you have gone down instead? Could you have done this? Technically, no, not with the resonance structure that's given, because this resonance structure has a single bond here, and that single bond would break if I did it that way. So we want to avoid breaking single bonds, right? So let's just go ahead and do it up towards the top carbon. What this is going to give us is this. This double bond's the same, this double bond's the same, but now I have a double bond O, and now I have a negative here. Is everyone following? Wait, what's the question, Johnny? Give us the answer. Russian hackers? I'm so confused, guys. What do you mean by two arrows? So, guys, what I mean by two arrows is that we have these patterns where positives move with one arrow, negatives move with two. Since this is a negative charge, I want to use two arrows. That's all I was saying. What are the Roman numerals referring to? Guys, we'll get there. That's what the question asked. It's a really long question, but let me just summarize it for you. What the question is asking is, after I draw my resonance structures, which Roman numerals will get a negative charge? Will a negative charge ever be on this Roman numeral here? Or will it be here? Or will it be here? Or will it be here? The only way we can know is to actually draw them out, okay? Cool. Cool, and I'm glad you guys are becoming friends online. You guys are all emailing each other. Cool. So guys, that's one resonance structure, but notice that this position was not one that had a Roman numeral. So this resonance structure doesn't really matter because it's not one of the answers to the question. But let's keep going. So now, what would be the next step, guys? If we wanted to keep moving this negative charge, two arrows, I would make a bond and break a bond. So now what I would get is something that looks like this. And I know that's right behind my head, so I'll try to go over here. Double bond, double bond. Now, this double bond is here, and this negative is here. Cool? They're hexagons, but thank you. So, so then the negative charge is there. So guys, is this represented by any of the letters? Yes, that would be Roman numeral 4. So then Roman numeral 4 definitely gets a negative charge. Are you guys getting this? Basically, you just have to match the Roman numeral to where a negative charge is. Cool. So now let's draw the other structure. So now the other structure would be that this negative comes here and breaks the double bond here. Let's draw that out. I'm really uncomfortable trying to get out of the way here, but it's fine. Can I draw a hexagon in this position? That's the question. Okay, double bond, double bond, double bond, negative. Okay, so see how now the negative charge went to this carbon, which is carbon 2. Okay, so there's a negative on 2, there's a negative on 4. Was in any of these structures, was there ever a negative on 3? No. 3 never got a negative charge because that's just not the way that the resonance structures work. Was there ever a negative on 1? Nope. So the answer here is that the only negative charges resulted on 4 and on 2. So the answer is going to be F. 2 and 4 are the only ones that get a negative charge. Okay? Did you get it right, Aisha? Josh, when you do the break it, why does that double bond form on the left part of the hexagon of the northwest bond of the NW bond? You didn't answer my question. Manuela, I'm sorry, I didn't even see it. Okay, so guys, this question, it's fine. I can hold for a few questions. We're done, but I see that some people are still a little confused. So Manuela, please just copy and paste that question so I can see it. And Josh, yeah, okay. Oh, how do I get the discount? Oh, Manuela, all you would do is you could unsubscribe, which means, oh, you would get it for the next, one. You'd get it for whenever you use Clutch in the future, you would use it. But you can contact our customer support and they can try to help you out, okay? And by the way, if you want help with customer support, it's Christy. She's awesome at Clutch Prep. She's our community manager. Cool? All right. Okay. For the last structure in red, can you move the negative charge to the right and move the double bond to the oxygen? So yeah, you could keep going. So there would be one more structure. That would be this. The negative comes here and then move the double bond to the oxygen. But that would just be going back to the original. So that's actually the last structure that I didn't go over because it's going back to the original, but you could totally do it. Cool. And Josh, I'm trying to understand your question, but I don't really understand it, okay? So what I'm going to do is I'm just going to keep going, and Josh, we can talk about this later. Like, I'm not going anywhere, okay? I do this full time, so I'll be here. Wait, if it goes back to the original, yes, Juan, I'm here. What do you want to know? Why is the negative charge not on the O? Oh, but it is. Look, when it goes back to the original, the negative charge goes back to the O. Okay, so in this resonance structure, what I'm doing is I'm showing that the negative charge is going to go back to the O. How long is this live session going to take, Manuela? I'm going to end right around 7, okay? Cool. I'm sorry, 7 Eastern time. If you're in different places, that means 50 minutes from now. Cool. So which are correct resonance structures for the following compound? Once again, we see that we have different answer choices, but let's go down and see what the multiple choice answers are. So, guys, once again, this is like similar to what we just did. Notice that I have a negative charge with an O next to a benzene ring, right? So that means, and by the way, this is called a benzene ring, which is our logo. So that's a good thing to know, just a random fact. So guys, we would expect that negative charges could form where? With the pattern that we just saw. The negative charge, I'm just going to do this a little bit quickly and see if you guys can follow. You could get a negative charge either here, or here, or here. How do I know that? How do I know that? Because remember that when you make a bond, you break a bond, right? So notice how that arrow would go down like that. And then when I do it again, when I make a bond, break a bond, I could do it down here. And when I make a bond, break a bond, I could do it up here. So those are the three structures that are possible by the negative going through this ring. And by the way, if you want confirmation that that's true, look back up at the last question and look, that's exactly what happened. The negative charge went here, here, and here. To the two positions right next to it and the one across it. Is everyone cool with that so far? By the way, this is very important for Orgo 2 people. Orgo 2 people need to be able to draw this. This is an important resonance structure. We're going to be doing negatives and positives together. Just hold on tight, okay? Cool. So guys, are any of these structures allowed by what I just did? Definitely one, right? One looks good because it's got the negative charge across from the double bond. What about 2 going here? That looks good too, right? Because that just means that this one would go here and this would go here. Okay? Yeah, unfortunately I do have another session at 7, Manuela. Tutoring never sleeps. I'm trying to help so many people. Okay? No, this is for Orgo 1 and for Orgo 2. Because everyone in Orgo 1 and in Orgo 2 needs to know resonance structure. So there are people, that's why some people don't remember Orgo that well, because they just started like a few weeks ago, okay? So now guys, the question is, can we make structure 3? Can we make structure 3? And the answer is, well, let's think about it. How could you do this? Because I would have to, let's say, put the negative charge here to make a double bond. But this N already has a lone pair, right? It already has a lone pair. So if I were to take this negative charge and make a double bond here, is that allowed? Is it allowed to put the double bond there with the nitrogen having that lone pair? What goes wrong there? What's that called? It's actually the worst thing you can call someone. It is an octet violator. Guys, that is just not right. And I feel terrible saying such a terrible thing. But that is an octet violator. You can't do it. Pardon my French, but that's just not allowed, okay? So then let's go the other way. How about if you put the lone pair from here and tried to move it in here as a double bond? Then what you would get is a double bond here. Is that allowed to make this thing? That one also breaks the octet rule, guys, because look, this right now has a lone pair on it already. Remember we talked about that? So if you did this, it's going to make a double bond. How many electrons is this carbon going to have? Way too many, because it already has, now it's going to have 4 bonds plus a lone pair. Okay? So basically what I'm trying to show you guys is that this is not allowed. But the only way you would know is that to draw it out and see if it works. And it doesn't work. Okay? Now there are tons of good questions, guys. I'm going to get to you. Don't worry. But does everyone understand why 3 doesn't work? I'm going to answer your questions. Don't worry. Is there any way to watch from the beginning, Alexis? Absolutely. You can catch this right after. We're going to put it online for you guys. And you can watch the whole thing all semester long. What happened to the sodium, to the Na? This is such a great question, guys. This comes from, you guys remember Chem 2? When you did titrations, acid, base, and stuff? What did we learn? Sodium is a spectator ion. Maybe you had Gen Chem with Jules here at Clutch, and you remember him saying that over and over again. So it doesn't even matter. We don't even draw it, because it doesn't matter, okay? What's another one? Which elements can expand the octet, Juan? Not carbon and not nitrogen. So right now we're dealing with carbon and we're dealing with nitrogen. Those cannot expand their octet. The ones that can are like sulfur, phosphorus, and sulfur, like the third row elements, but we don't have those here, so you don't have to worry about it. So then we've got, where is Jules? Well, Jules is here, just helping other students. Okay, so Jules was here earlier actually. So can I explain why 3 doesn't work one more time? Yeah, it's like basically group, well not group 3, it's period 3 and below. Okay, or row 3 and below can expand their octets. So guys, one more time, just because I want, this is so important. If anyone, this is probably one of the most important things we're going to learn today. Why is this not included? It's not easy. You have to draw it out. The reason is because there's no way to put a double bond between the carbon and nitrogen without breaking the octet. So it's very important that you understand that if you did this, you'd break nitrogen's octet. If you did this, you'd break carbon's octet. So this is not a possible structure because you can't break the octet. Okay? So then the answer, just to go back to get the right points, it would be C, 1 and 2. And I hope that that helps. I know someone wanted to look at that one more time. Cool. All right, guys, draw all reasonable resonance structures for the radicals shown below. So we're finally on to radicals. So our rules 1, 2, and 3 still gonna apply to radicals. Hell yeah. They for all resonance structures, you use those rules. The only thing that's gonna change is pattern. Now we're gonna finally do pattern number 3. Numero 3. What is pattern number 3? Okay, I think we will. I think we're gonna finish, Prita. So pattern number 3, just so you know, Brianna, the 3 rules were the very first thing I talked about today, and when we replay this, you can catch them all. They're right at the beginning, okay? So pattern 3 is gonna be 3 arrows. And it happens only with radicals. So this is the one for radicals. And pattern 3 says that you have to use fish hook arrows or half arrows, because in this case, what we're doing is we're only moving 1 electron at a time, not 2. So the pattern goes like this. You start from your radical, and you put a half arrow towards the bond, and then you split your double bond into 2 different electrons. 1 electron joins this one over here, and 1 electron goes over here. So what we get is 3 fish hook arrows. Okay, and this is how you always move radicals. So some people, it turns out, your professor just skips radicals, and that's fine. And in that case, you have 2 questions, and we'll be over with them soon. Still stick around, because we've got other stuff coming up. But most people have to do radicals in Orgo 1, so that's why I'm talking about them here. If you're in Orgo 2, you definitely need to know this, because you have a whole chapter on radicals. So what would it look like afterwards? You would have your new double bond here and your new radical here. Basically, every fish hook arrow moves 1 electron around. So you're taking 2 electrons and you're making the first double bond, and there's 1 more on the side. Okay? Cool. So, guys, radicals are actually some of the easiest ones, though, because the pattern doesn't change. You don't have to worry about lone pairs. It's always just double bonds and radicals. So it's very straightforward. All you have to do is draw your arrows starting from the radical and going to the double bond. So it would be like this. 1, 2, 3. So let's draw that one. And that would put my radical here. And then we would do it again. We would do towards this one. 1, 2, 3. I have to draw smaller so it fits. And then that would give me double bond here, radical here. Okay? Now the question is, we just moved it to those double bonds. Is there any way to get it down to this double bond here? Could I get it to like make a radical down here or something? No, guys, because it's not close enough. For resonance to exist, they need to be adjacent to each other or next to each other. This double bond is so far, it can't participate in resonance, so you would never put the radical there. It would not move there. Okay? So actually, guys, this is your answer. It would just be these 3 structures. Okay? Because you can't ever get the radical to the bottom. Cool. So let's do one more. And by the way, guys, one more for radicals, right? And notice that now we have 3 double bonds, but now you guys tell me, do you think that it's going to go through all the double bonds or just a few of them. We have this one, we have this one, and we have this one. And in like advance, can you guys tell me, will this radical flow through the entire molecule, all the double bonds, or will it skip any double bonds? Tell me that right now. What do you guys think? Notice it's going to go through all of them because they're all next to each other. They're all adjacent. So since all of these are next to each other, it can flow through the whole thing. And that's a concept that we call conjugation. Okay? Conjugation means that you can flow through the whole thing. It's all conjugated. But up here, notice that this double bond was too far away, right? So this one is called not conjugated. And just so you guys know, if you're in Orgo 1, your professor may not be asking you to determine this yet. But if you're in Orgo 2, you definitely need to know this. Prita, the difference between conjugation and hyperconjugation, huge difference. So I can't even explain that here because they're totally different things. They have similar names and that's where it ends. Yeah, exactly. It's very, very different, okay? Cool. So guys, I'm just going to draw these really quick. So it would be boom, boom, boom. And that's going to give me double bond, radical. And then I would do boom, boom, boom. And this would give me double bond, radical. And I'm going fast, so if I mess up or if I'm missing something, please let me know. I need your help. So then finally we have the last one, which would do boom, boom, boom. And that would be double bond, radical, CH3. And there you have it, guys. Those are all the resonance structures. Okay, because your radical got to the very end of the road. There's nothing else that it can do. There's nowhere else for it to go. This molecule was conjugated or was able to resonate through the whole thing. So then we're done. We drew all of the resonance structures. And I'm really glad that you guys think that this is making sense, which is great. Some of you guys don't even need to know radicals. I would say the majority of you do. That's why we went over it just in case, okay? Cool. So are you guys ready for, oh, there's this last one. This is so easy. And then we're going to do major and minor contributors. So just so you guys know the way this is working, one last multiple choice, and then we're going to do major and minor contributors, which is the question of which of these resonance structures is the most stable, or which one is the highest contributor. You have no idea how to answer that right now. I'm going to give you the rules. The rules are coming, okay? Cool. So which pair represents resonance structures? So guys, I'm going to move down here. And you guys can help me cross out. I want everyone helping me here. I want to see this chat thing blow up. Which of these can we cross out that are for sure not resonance structures? And tell me why. What is not a resonance structure here? Okay, so I see a lot of people saying 1. Why is 1 not a resonance structure? I know I'm in the way. I'm sorry. So yeah, 1 can't be because notice that I have a new H over here. I'm moving atoms, so definitely not. Let's move down so you guys can see 2, 3, and 4. Okay, so then let's see. I see some people saying, Irene said 3. What do you guys think? Can the positive charge move from here to here in a resonance structure? What do you guys think? No, right? Because notice this is what's happening. Right now, how many hydrogens do you have? You have a blue hydrogen here. Let's just use, blue, and then 2 red hydrogens, right? Positive means you're missing a hydrogen, right? After you move the positive, what are you going to have? Now you're going to have 2 blue hydrogens and 1 red hydrogen. That doesn't make any sense. We just moved atoms. We just moved hydrogens from place to place. So this is also not allowed. And guys, you could know this. Yeah, it's illegal. This is one of the worst things you can do in your life, is try to do this resonance structure. And I'm not always going to be there to bail you out if you make those kinds of decisions, like self-destructive decisions. But listen, you can't do that because there's no double bond to move it, right? So you just can't resonate like that. Cool. Let's go down to 4 really quick. I'm trying to do these in a specific order. So 4 is a radical. So how could we make this radical look like this one? The only way that we could resonate it is like this. Single bond, not single bond. Fish hook, fish hook, fish hook. What that resonance structure would give me is a double bond here and a radical here. Does this look anything like this? This is a mix, guys. This is us putting all the concepts together. This is us putting the positives, the negatives, and the radicals all together in one question to see if you're comprehending it. So the answer is no, the double bond's in the wrong place, right? So this is not a resonance structure. So then 2 is the answer. 2 is the one that is a resonance structure, but can you guys show me what arrows you would use to make 2 into that one? How could you draw your arrows so that it becomes this second thing? So what you could do is you could take the electrons from the O and make a double bond. And then after you make that double bond, you have to break this bond, make a bond, break a bond. So then you would break this bond and make a negative charge there. And what that would give you now is that, let's say this electron is blue, now it's going to be here. And let's say that now these electrons are green, now they're going to be here. Okay, does this make sense? So this is the right answer, and this is a cumulative question that basically combines everything that we just learned. Cool. Awesome, guys. So I feel like I'm feeling better about you guys drawing resonance structures. Let's go ahead and talk about major and minor contributors. So this question is a little different from everything we've been doing. It says, create the electron arrows. This comes from, I think this is from Dr. Fields at USF. Go Bulls. Yeah, she puts these questions on Orgo 1 and Orgo 2 because Dr. Fields loves to talk about resonance. So create the electron arrows needed to arrive at the other resonance structure for the following molecule. Construct a new resonance structure produced by the shift, and then classify each one as major, minor, or equal contributors. So for this, guys, we're going to need new rules. And these are the rules I'm going to teach you right now. Are you guys ready? Pen and paper in hand. So how do you determine major and minor contributors? Okay, there are 3 things that tell you if something's minor. 1 is if octets are not filled. If your octets are not filled, then it's going to be a minor contributor. 2 is if charges and electronegativity, I'm just going to put En, disagree. I'll explain what that means in a second. 3 is if you have a separation of charges. All of these things are going to make it minor. These are things that make it minor. So the way that this works is you figure out which ones are minor, and then the ones that are left over are your major contributors. Okay? Now, I think that you guys get octets are not filled. It means you don't fill your octet. Separation of charges means that you have a lot of extra charges. That's an important one. If you have a lot of extra charges, it's not stable. What does it mean that charges and En disagree? What it means is, let's say you have these elements, carbon, nitrogen, oxygen, fluorine. You guys recognize this part of the periodic table? This is the part of the periodic table where electronegativity goes like this and like this. You recognize that? Cool. So what if one of your resonance structures has a negative charge on the carbon? The other resonance structure has a negative charge on the O. Which one is going to be better? Which one is better to have? The negative charge on the carbon or the negative charge on the oxygen, and why? O is better because it's more electronegative. Electronegative likes O, and carbon likes positives more. So in the same way, what if I had a positive on the carbon or a positive on the oxygen? Which one is more stable? To have positive on oxygen or positive on carbon? Right, so the more stable ones, guys, are going to be this one and this one. It's more stable to have a positive on a carbon because it's more electropositive, and it's more stable to have a negative on an O because it's more electronegative. Get what I'm saying? So this helps you determine which one is more stable. Cool? But the only thing, guys, is that these do go in order. You have to look at rule number 1 first. The first most important thing is that octets must be filled. If your octets aren't filled, don't even look at rules number 2 and 3, because that's the most important one. And we go in order. So let's go ahead and try to see if we can apply that to this question. And I bet you didn't learn it that way in class, but that's why I'm here, to help you guys. So guys, the resonance structure here should be easy. We've done this a bunch of times. It would just be that these electrons come down and make a double bond here. So let's go ahead and draw that here. I'm going to get O, H, now with a double bond here, and now the positive switch to here. So those are the rules for minor. Octets not filled, charges and electronegativity disagree, meaning that it's the opposite of what we talked about, and separation of charges. We're going to apply it in a second. But is everyone cool with this arrow so far? And by the way, it says, create the electron arrows needed to arrive at the other resonance structure. So I'm going to go ahead and put the other arrow going back, which would be this, to show both sides. Cool. Awesome, guys. So now, the first question, how do we determine which one is minor, major, equal? Let's look at octets. Do both of these have their octets filled? What do you guys think? Are any of them missing their octet? So let's go one at a time. Let's go one atom at a time. And also, let's draw in all the lone pairs. This oxygen now has one lone pair instead of 2. So, does this oxygen have 8 electrons? Yes. Does this, because remember that a bond or a lone pair counts as 2. Does this carbon have 8 electrons? Yes. Does this O have 8 electrons? Yes. Does this carbon have 8 electrons? No, because notice that it's missing one of the hydrogens, so it only has 3 bonds, so it has 6 electrons. What does that mean? That means that one of these structures is violating the octet rule. It's not filled, so that means that this is going to be my minor contributor. And then by process of elimination, I know this is my major. Cool? That wasn't so bad. It's, yeah, well, I don't know. The saddest atom is actually the carbon, because the carbon is missing its octet. So we know that this one is not going to contribute much, and the one on top of me is going to contribute more. Does that make sense? Cool. So let's go down and do another one. Which of the following resonance structures is the least important contributor to the resonance hybrid? So guys, this is an opportunity for you guys to apply what we've been talking about. Are there any that we can cross out because they're minor? Let's cross out 1, 2, 3, or 4, cross them out because you think that they're too minor and they're not going to work. And tell me why. I see a lot of people don't like 3, and actually I see why. Well, it's not, oh man, I was so happy when you said 3, but then you said separation of charge. Separation of charge is the lowest priority rule. First, we look at all the octet violators, right? Remember, what's the worst thing you can be? An octet violator. Let's knock those out first. So 3 has an octet violation, guys. Did you not notice that? So you have to cross it out. What about 4? 4 also has an octet violation. Cross it out. Okay? Then these guys over here are, all their octets are filled, right? So we know these are going to be on the major side. So these are major. These are on the more major side of things. And these are on the more minor side of things. Okay? So now, what's the question asking for? It's saying which one is the least important contributor. So we know that the answer is either going to be 3, which is minor, or 4, which is minor. Okay? Is this making sense, guys? I know that I crossed out 3 and 4, but I was saying which ones are stable. Those are more stable. Now we have to look at which one is the most minor of the two. So notice that 1 and 2, are they both octet violators? Or, I'm sorry, 3 and 4, are they both octet violators? Yes. So this is violating the octet here. This is violating the octet here. So those are actually equal. So now we have to go to the second rule. So the second rule says difference in electronegativity, okay, and charge. So notice that here I have negative on carbon, and I have positive on carbon here. Here I have positive on O, and here I have negative on O. Which combination is better? To have the positive on the carbon or to have the negative on the carbon? Which one is better? To have O have a positive charge or to have O have a negative charge? Let's even draw it out. C, N, O, F. And then here we have, let's draw it again. C, N, O, F. Okay, so on the first one I put negative here and I put positive here. On the second one I put positive here and negative here. Which one makes more sense? To have the negative, to have the 3 pattern or the 4 pattern? So doesn't it make more sense that 3 is the most minor? Because it's the one that has the mismatch, right? Remember that mismatch is bad. Right now, fluorine wants to be the most electronegative. But for 3, the O has a positive. Now notice that over here, the O has a negative. For 4, that makes more sense. So that means that this one is a little bit more major, and the right answer is 3, is the most minor. Because it's the one with the most mismatch. Does that make sense? Because we want to make sure that your electronegativity and your charges are agreeing. Cool, so 3 was our answer. Sweet, guys. So we're just using the same rules. We never even got to separation of charges, which is the third rule, because the rule number 2 solved it for us. Okay, so remember to look at them in order. Cool. One contributing resonance structure to a resonance hybrid is given. Curved arrows are used to show how electron pairs move to generate a second resonance structure. Everyone knows this. Cool. Everyone knows this now. You guys have all done this. So structure Y, it says which statement is true. Structure Y and the given structure are of equal importance, structure Y is less important, or structure Y is more important. So what we need to do is draw out structure Y and then see what we find. So structure Y, they gave us the arrow already, so it's really easy. So it's just going to be this. It's going to be that now I have an extra lone pair on the nitrogen, and now I have a positive here. Right? Does that make sense? Because notice that, for example, this used to be the electron's green, and the positive charge is blue, right? So what happened is they swapped. Now the green is here, and now the blue is here. Cool. So guys, notice that before we were dealing with like a bunch of different structures. Here we just have two. You have to tell me what's the first rule that we look at. What's the most important rule? Octet violator, right? Octet violator. So are any of these breaking their octet? We can go one atom at a time if you want. So let's go to atom 1. Is atom 1 breaking its octet? It's fine. Atom 2, is it breaking its octet? No, it's fine. They both have 8 electrons. Atom 3, does this carbon break its octet? Yes, it does. This one is sad, guys. This is a sad carbon, right? Because it's missing its octet. And then finally, this N is fine. But this structure is going to be minor because that carbon is sad. He's sad again. I know, it's like always the carbon. What did he do to deserve this, guys? He's minor, so that means that this one is most important, which means that this one, Y, is less important. So the answer would be B. Structure Y is less important than the given structure. Cool? See the pattern to this? We're just applying the patterns, applying the rules. You can get it right every single time. Okay? I think someone asked earlier a question that I was about to get to. They said, like, why can't carbon occasionally break the octet? It can, and it happens all the time. Believe me, you're going to see carbons with positive charges all the time in organic chemistry. They're just not very stable. So that's why they're the least important resonance structure is the carbon with the positive. But it happens all the time, believe me. Cool, I'm really glad I can help with the explanations, guys. So this is easy. This also, it looks like it also comes from Dr. Fields because it's exactly the same combo. So you guys just have to draw the resonance structures and tell me minor and major. Okay? Now for the sake of time, if we weren't so short on time, I would just wait for you guys to draw it. But what I'm going to do is I'm going to draw them all and just explain it because we want to get through all the problems today. So first I'm going to draw the backbones, or what I call the framework, so that you guys can tell me where to add stuff. Cool. Notice that I'm not including any double bonds, any lone pairs, any negatives, so you guys can tell me what to do. So what should be the first step of the first resonance structure? It should come from where and go to where. We're going to do colors again. We've got yellow, we got green, we got blue. Where should the first arrows come from? Please let there be a problem with saturation charge. There might not be, I'm not sure. We'll see. So what should it be, guys? I don't see. Yeah, but give me some colors here. There you go. Blue to green. It should go blue to green, right? And how many arrows should it be? 2. So I should go from here to here. Notice that everyone can know that because it's just applying our rules. So then what that means is that this one didn't change. This now has a double bond, and this now has a negative charge. So now blue is here, green is here, yellow is here. What's going to be the last resonance structure? Yeah, make it and break it. Exactly. What's going to be the last one? Blue to yellow. Boom, boom. We're done. So then what that gives us is this is now a double bond, this is now a double bond, and now this is a negative charge. So now I have green, blue is here, and yellow is here. Okay? So what I'm basically doing is I'm trying to show the flow of electrons, right? I'm not sure if that made sense to you guys. Maybe I should have flipped it, because that's the way I've been doing it all day. No. What did I feel like I flipped my colors, guys. I'm sorry. Because I was doing it a different way before. So this would be blue. I'm sorry, guys. I feel a little embarrassed. And this would be green, because what I'm trying to show is that it's flowing. And then now this is still blue, and now this is still green, and this is yellow. Does that kind of make sense? I'm trying to show how it's flowing through the whole thing. Cool, but anyway, we're done. The negative charge is now all the way at the end, and that's the end of the problem. Did we add an extra lone pair on the O for the third? Absolutely. So what happened was that this O used to have 2 lone pairs because it was neutral, and now it has those 2, plus it has the third one that came from this bond here that broke. Okay, that's how it turned negative. Cool, guys. So this is the part that you guys should know. Now what we have to do is predict major and minor. So can you guys tell me how you can tell if any of them will be minor or major? For example, do we have any octet violators? What do you guys think? Yeah, exactly. Always check your octet first. So maybe the second one is an octet violator. Where? Which atom? Yellow? Nope. Yellow is fulfilling its octet because every atom has 8 electrons. Green also has 8 electrons because, for example, the green, this is what it looks like. It's an H and it's a lone pair, right? With a negative charge. That means negative charge. Which, by the way, means 8 electrons because 8 electrons, every single bond counts as 2, every lone pair counts as 2. So if you count them all up, what you're getting is, my pen just froze, so I'm trying to figure out how to get it back. But while it hopefully gets back, it would be 2 going up to the hydrogen, 2 going down to the yellow, 2 going down to the blue, and then 2 in the lone pair. So that's fine. So guys, the answer, and I'm gonna need Jonathan, so I'm not sure if Jonathan is watching. Please help me. We might have to restart this tablet because my pen just stopped working. Oh, wait. Is it coming back? Please. Yeah. Come on. Come on, guys. Let's pull for this tablet together. We need to finish today's lesson. How many more do we have? We have 1, 2. Yeah, we need to finish. We're so close. Okay, it came back. Woo! Oh my God, I was sweating a little bit. Okay, it came back. Thank you. Your prayers were heard. So guys, the answer is that all octets are filled. Okay? So now we have to check charges and electronegativity. So what we notice is that we have, basically, just to simplify it, we have carbon negative, we have carbon negative, and we have oxygen negative. Can you guys tell by the charges and electronegativity if one of them is going to be better than the other? So what we know is that we've got carbon, nitrogen, oxygen, fluorine. And what we know is that the negative wants to be as close to the fluorine as possible. So that means that this is my major and the other 2 are my minor. Okay? And just so you guys know, you might be asking, well, which one's better between A and B? Guys, they're all pretty much exactly this. They're both exactly the same. They're just less than the last one. Okay? Yeah, minor will be both of them. It's possible to have more than one minor. It's also possible to have more than one major. Cool? Let me know if that made sense. Cool. So then here's another one. Now this one has a nitrogen, which will be good because we get to work with a new type of atom. And let me just answer this question really quick. Yes, the negative charge, I didn't draw it. Well, my pen stopped right when I was drawing it. It's right there. So it's on a carbon. So then it's minor. Cool. So guys, this is the same exact question, just worded a little different. We have to draw our resonance structures, and then we have to predict major and minor. So let's go ahead and draw that now. I'm just going to draw the octagons. In this case, I am drawing octagons. And you guys tell me what it should look like. Cool. So how many arrows should I use? Oh, let's also do colors. Blue, green, yellow, and pink for this lone pair. Cool. So what should the first one look like? And what color to what color should I go from? So guys, I should use one arrow since I'm doing positives, and I should go from green to blue. So then I would do basically this, and what I would get is a new double bond here, a new positive charge here, and a new double bond here. Cool? Awesome. Let's go ahead and do our colors again. This time I am going to swap the colors because they literally switch places. So the green is now here, the blue is now here, the yellow is here, and the pink is here. Cool. So now what should we do? So guys, now what should we do? We should switch blue and yellow, right? With one arrow. So let's do that. One arrow over here. So what that's going to give me is double bond, double bond. And now this has a lone pair, but it would be positive. It would be positive because it's missing an electron. It's missing the double bond that it used to have. So now this is green, now this is yellow, and now this is blue right here, and this is pink. Cool. So guys, that's actually our last resonance structure because you can't do anything over here, right? Like I can't just like break a bond and make a new resonance structure. So these are our 3 resonance structures, okay? Now, which ones would be minor and major and why? Yeah, so guys, we have to look at octet violators, which are, you know, the scourge of the earth. And what we would find is that this is an octet violator. By the way, carbon with a plus charge is always an octet violator. And some other elements with positives are not. So for example, N with a positive is not necessarily. N with a positive, O with a positive is not necessarily, but this is definitely an octet violator here, okay? Now the N, is it an octet violator? Yeah, this one's, hey Rachel, welcome from TAMU. You're a little bit late, but it's all gonna be rebroadcasted later tonight, so you can watch it as many times as you want, but I'm really glad that you joined. So N is also violating its octet, right? So guys, like, all of them are octet violators, so can we choose minor and major yet? No. So we need to go to the second rule. They're all octet violators. So let's go to the second rule. We've got C positive, we've got C positive, and we've got N positive. According to electronegativities, C, N, O, F. What's better? To have a C positive or to have an N positive? Right? Wait, yeah, exactly. To have a C positive, because as you go to this direction, you get more negative. As you go this direction, you get more electropositive. So carbon would prefer to have a positive rather than nitrogen. Does that make sense? Because remember, if you want to go negative towards the F and you want to go positive towards the C. So that means, guys, that this is a rare situation where carbon with a positive is actually major. And nitrogen with a positive is minor because of the fact that you're breaking nitrogens, you're putting a positive charge on nitrogen, which is not its electronegativity preference. Cool? Awesome. Good job. I have no idea what that word is, but yeah, C plus is better. Cool. Is there a better than the other? Guys, they're both the same thing, pretty much. When is it equal? Guys, it's equal if they're both exactly the same. So, for example, yeah. Guys, I'm gonna do a 10-minute extension just for you, which means the other class is gonna have to hold, but we're gonna try to extend it. Yeah, it's fine. It's fine. Okay. The other class is gonna have to wait for 10 minutes, okay? Because I really want to finish with you guys. Cool. So just so you guys know, when would it be equal? If you had something like this, like a negative here. Oops. I don't know, like this is a possible structure. if you had this situation. Ooh, no. Oh my God. This is for carbonate. This is a very common resonance structure that some professors give you. So it's, see how in this case they're both the same thing. I have negative negative on O, negative negative on O. These would be equal. Does that make sense? Because they're the same thing. Okay? Oh, cool. I get it now. I get the electronegativity thing. Cool. So guys, we have our last problem. So I'm just going to go ahead and say one more time that thank you so much for joining me. This is a two-part series. So if you found today helpful, you only got half of it. We're going to do the next part next week, and guess what it is? You guys were wondering what is it going to be? So today was mechanisms. I'm sorry. Whoa. Oh no, I gave it away. That's not what I meant to say. Today was resonance. Ugh. I was waiting for like the grand reveal. Next week is going to be mechanisms. Okay? Now you might be saying, Johnny, do I need to know mechanisms? Yes, like mechanisms are like the most important thing in organic chemistry. Do you need to know it for chapter 1? Maybe not. Chapter 3? Hell yeah. Like by the time you're getting into chapters 2 and 3, you need to know mechanisms because this is going to help you with acid base. This is going to help you with all types of reactions. It's the basics of reactions. And guess what? The rules that we applied from resonance apply to mechanisms. It's actually, that's why this is part 1 and next week is part 2, because we're going to be referring to a lot of the rules we talked about today to talk about intro to mechanisms, okay? So I just want to let you guys know that's going to be same time, same place. I hope that even you guys tell your friends there's going to be an awesome lesson. They have a whole week to watch this one so they're not lost. And then you guys can all join me next week, 5 p.m. Eastern Standard Time. If you're out west, it's just, you know, calculate your time zones. That's the only thing you got to do. And we'll do mechanisms, which is part 2. I also want to let you guys know, Friday. So it's going to be Friday at 5 Eastern. Okay? 5 p.m., not a.m. And guys, I also just want to let you guys know that what I do full-time here at Clutch is I make video versions of your textbooks. So basically, I make a bunch of awesome videos to help explain your textbook better. And I've helped a lot of students get better grades through just really helpful explanations and helping to break things down very simply. Also, a new thing that we have this semester, which you guys are going to get really excited about, yeah, I'll send out a text, is exam reviews. So guys, for the first time ever, I'm trying to make exam reviews for everyone in the country. Isn't that crazy? Isn't that like mind-boggling crazy? So what this means is that there's a little tab in Clutch Prep where you can click on exam reviews, and then it says submit your info. So then you drag in info about like what chapters are going to be on your exam, what topics are going to be on, what did your professor tell you to skip. You drag in like practice questions, PowerPoints, whatever. Give me as much information as possible. And what I'm going to do is I'm going to record an exam review for you guys that will be questions that are relevant to help you get a better grade. So imagine these 20 questions on resonance. Imagine if we did this for 3 chapters, where it's like resonance, formal charges, hybridization, whatever. Like that's what we're trying to do. So the better chance of getting an exam review is to submit the most information possible so that I can help you. And the first exam is also free. So like crazy, I'm gonna do all that for free. I'm not gonna sleep, it's fine. And then one more thing is that the coupon code specifically for you guys that are watching either part 1 or part 2 is arrows20. And what that's gonna do is it's gonna give you 20% off any part of Clutch that's paid. You might just wanna use the free parts, which is fine, a lot of it's free. But we do have to pay the bills, keep the lights on, have a lot of people working to try to make studying science better. So it's 20% off a subscription to some of the paid content, which is like practice problems and exam 2, exam 3, stuff like that. Cool. Cool. No, it's not email, guys. Don't email me all your notes. It's in Clutch Prep. It's a little button that says exam reviews, okay? So let's go ahead and just do this last problem. And then if you guys have any questions about Clutch, I'm happy to, or we might have time for one extra problem at the end, okay? So guys, our resonance structures here would be very easy. It would just be, this one goes here. And then this is a lone pair here, so this can come down here, just using the one arrow pattern that we've been talking about all day. And this is going to give me double bond here, positive here. And then it says, circle the major contributor. Circle the major contributor. So what do you guys think is going to be the major contributor? And now I'm going to try to answer some questions while you guys tell me. So just so you know, if you're from USF, your first chapter is free and your first exam is going to be free, okay? So some schools are slightly different because we do professor-specific stuff. So it just depends on what university you go to. But cool. Guys, so it turns out we have to look at octets, right? Are any of these octet violators? Yes, this is an octet violator. This is an octet violator. Do we have any octet violators here? All octets filled for this one. So that means that the major contributor is going to be the one that I just circled. Okay? And the other ones are minor. Okay? Guys, it was such a pleasure helping you guys with organic chemistry today. Organic chemistry is supposed to be fun, okay? And I'm going to try to help you guys throughout the semester. It was just like a privilege, and I really hope to see all you guys next week at our mechanisms review, where we're going to apply a lot of these same rules to actual reaction patterns, okay? I'll see you guys at 5 p.m. Eastern Standard Time next Friday. Be here. Don't miss it. Okay? Cool. Awesome, guys. And if there are a few other questions, I'm happy to help for a little bit. Yeah, I'm over my time limit. I have to go. All right, guys, if you have any questions, the chat bar of Clutch is always open. You can always just like type in a question, and I'm here all day. I can help you. Bye, guys. You guys are awesome. Let's crush Orgo this week. I'll see you guys next time.